that I claimed that if we do the path integral over all gauge fields up to gauge equivalence, in this case for when the group is U1, e to the integral of a dA, and then so last time we were studying the 2-point function of these observables, which is the integral of this gauge field over a curve over a knot in R3, and we claim that this expression is equal to, up to some normalizing constant, the Gauss linking number. So we also saw that this Gauss linking number, this does not change if we vary K1, K2 continuously without making them cross. So an expression like this, something which, if I start with a knot or a link and I produce a number which doesn't change if I vary them a little bit, it's called a link invariant. So what I want to do today is I'm just going to spend most of the time computing the Chern-Simons propagator and explaining why it leads to this expression. But the first thing I want to point out is why formally, by looking at the path integral, we would expect this expression to be not to change if I vary K1 and K2. Well, from the path integral point of view, and especially when we move to non-abelian gauge groups, the more natural invariant is not just the integral of a around a knot, it's the exponential of that. So it's what we call the Wilson line. Now consider, and let's discuss why that should be invariant if I change my knots a little bit. So consider the path integral. And here I'm going to put a Wilson line that's where these expressions, WKI, these are Wilson loops on some closed curves. So I've only given you the formula for the abelian Wilson loop so far. Later today or on Thursday, I'll give you the formula for the non-abelian one. It's kind of similar. So we can ask, if we suspend our disbelief and pretend that we actually believe in the path integral, which I kind of don't, but that's okay. Then you can ask, does this, if we look at this expression, why should it, how does it depend on the positions of these guys? If I vary one of the knots a little bit, I just wiggle it a little bit, does it change? we wiggle K1, does this change? The answer is that heuristically, no. This is because the path, the Chern-Simons Lagrangian, is invariant under all diffeomorphisms. And the Wilson loops these are diffeomorphisms covariant. That means if I choose a diffeomorphism which takes one loop to another loop, then it takes this observable to the corresponding Wilson loop observable. So if, say, phi is a diffeo, then phi applied to the Wilson loop observable, because phi acts on the space of fields of Chern-Simons theory and leaves the Lagrangian invariant, so I can take another observable and see whether or not it's invariant. And it will not be, but it will transform into the Wilson loop where the transformed knot. Okay, so how do we see that the path integral did not change? Well, what we do is we choose a diffeomorphism which leaves all the knots fixed except for one and moves that in your chosen way. There always is such a diffeomorphism. So if we vary, say, ki to ki tilde without introducing any crossings, so a continuous variation, then we can find a diffeomorphism phi. So phi of kj is equal to kj. J is not equal to I. And phi of ki is ki tilde. So since we're pretending, since we believe for now, well, sort of, that the functional measure is diffeo invariant, then we find that the integral over gauge fields now, I'm going to apply this transformation phi, which leaves the measure invariant. And it's just going to, well, it leaves all the operators invariant except for this one. Okay, so this is the heuristic argument for why the study of Chern-Simons theory will lead to invariance of knots and links. And what we're going to get to soon, I hope, is so Witten became interested in Chern-Simons theory in the 80s because Jones had come up with some new invariants of knots and links. And Witten proposed that they should be realized by this path integral. And the fact that they were invariants is realized by this argument.
Sorry, can I repeat why the Chern-Simons action is diffeomorphism invariant?
Right, so the way I like to think about this is to write down the Chern-Simons action as a 3-form, I didn't need any structure on my manifold. It's something on any manifold, without any metric or anything, I can define wedge and D. And the Chern-Simons action was defined with just with that. So it's because of that, it's invariant under all the symmetries of the manifold. I forgot to say, of course, it must preserve the orientation.
So the default must be a symmetry of the manifold.
Yes, that's what I mean. A diffeomorphism, her manifold is OR3. And the diffeomorphisms are just the symmetries of OR3, which don't preserve any structure. So like, the key point is to write down the Chern-Simons action, I did not need a metric tensor. Yeah.
Sorry, this might be very basic, but under a diffeo, how does A change? Or
It changes by pullback.
A changes under the pullback? Oh, okay.
Yeah, so if I phi from OR3, OR3, A, I get sent to phi star of A. So we can really write it out quite explicitly. So why is it diffeomorphism invariant? It's in the abelian case. So A wedge dA gets sent to phi star of A, wedge D phi star of A. And the rules of pullback in de Rham theory means we can move it past D. And it also behaves well with vector wedge. And then the integral over OR3 of A wedge dA is equal to the integral over OR3 of phi star A wedge dA. Because if in coordinates, phi star gives you a Jacobian factor. Makes sense, like on any 3-form.
And so phi star of the loop is just exponential of the integral of the phi star of A?
Yeah, I'll run that curve, and it's the same kind of argument. I mean, the key point is that when we're dealing with differential forms, we don't need to choose a coordinate to write the integral. That's the only fact we're really using. The integrand is a 1-form, and the integral is independent of what coordinate I use to write that 1-form. Yeah?
What is the pullback you mean with the differential? Sorry.
Okay, so that's something you can see. Yeah, you're right that I didn't, like in a review of differential forms, I should have explained this point, but I didn't. So I think it's worth seeing it then. So if I have a form omega I1 in dx I1 okay, dx ik d omega sum del omega del xj I1 ik dxj dx I1 wedge dx ik. phi star d omega is some, well, I'm going to do a little manipulation, but in the end, we're going to find it's down to the chain rule. Because I'm going to be differentiating something omega of phi of x. Sorry, phi of y. dxj xik. On the other hand, sorry, here is d phi j. On the other hand, d of phi star omega, well, let's first write down phi star of omega. That means I replace this x by phi of y. So this is omega I1 ik phi 1 of y phi n of y. Let's support up a little bit. And then here I have d phi I1 wedge d phi ik. And then I'm going to take d of this. So that means I do d dyl wedge. Okay. So now if you stare at these two expressions, you'll find they're almost the same. This part over here is kind of the same. It's like d phi I1. So this part over here is kind of the same. So they differ, except this one differentiate with respect to x, and then I multiply it by d phi j, which is d phi dx, or sorry, d phi dy dx. And this one is differentiated with y, and I multiply by dy. So then they are the same because of the chain rule. So that might be a good exercise to do carefully. Okay, any other questions? Yeah.
Can I ask, yeah, this is again very simple, but say if I have K a loop thought of as a map from the circle into M, then under a diffeomorphism that goes into loop phi after K, right? And I take the pullback of that map, like that map. With that map, I pull back the form now of phi star of A.
Yes.
Is that the same as K star of A? So phi after K, everything star of phi star of A is the same as K star of A?
Right, let me write out your question. So I have K S1 to OR 3, phi OR 3 to OR 3. And the first Wilson line is going to be the integral over K of integral over S1 of K star of A. Right, and then the second one, and you want to compare this to the integral over S1 of phi composed with K star of A. Okay? So now you're asking is, how does this compare to K star phi star of A?
Well, I thought that we were going to do phi after K star of phi star of A.
I think I might have had an inverse wrong, an inverse.
Oh, okay.
Well, the fact is, phi composed with K star of A is K star phi star of A. Right, so so what this is telling us is changing K to phi composed with K is the same as changing A to phi star of A. Okay. So possibly this is not exactly what I wrote down over there. Perhaps I should have had a phi inverse somewhere. But does that answer your question? And then, sorry, I should have done that over there in more detail. So here we see applying the diffeomorphism. I think the mistake I made is that applying the diffeomorphism should have been phi inverse star rather than phi star. Yeah, applying the diffeomorphism is the same as changing the knot. Okay, any other questions?
Does the pullback will change right around chronology? Because it's what you just told me is a chain map.
Yes.
What kind of map will be between those two cohomologies?
Oh, great question. Well, so if my diffeomorphism is connected to the identity, it will not do anything on it will be the identity on cohomology.
Okay.
So the map on cohomology is like a topological invariant of the diffeomorphism. It doesn't change if I change my diffeomorphism a little bit.
Okay.
So it's there's some fun math related to this. So, for example, you can figure out how many fixed points your diffeomorphism has by computing its eigenvalues on cohomology. To the left, it's fixed point theorem. So you can build topological invariants of the diffeomorphism this way. Okay. So if everybody's reasonably happy, and sorry I went too fast, so I want to try to explain how to compute the propagator of Chern-Simons theory. So let's think back a little bit to something much more basic, and like how do we construct the propagator for a free field? So if we consider it's a free field with a Lagrangian, integral phi Laplacian phi, then to compute the propagator, we introduce a source. And we try to solve the equations of motion in the presence of the source. And then there's some factor there. And if I solve this equation, the solution to this equations of motion will be given in terms of an integral expression when the integral kernel is the propagator. So the solution to this equation, well, I need the Laplacian of phi equals j, which is solved by phi of x is equal to the integral over x, y, g of x, y, j of y, and g of x, y is equal to the Green's function. Okay, so for Chern-Simons theory, we're going to do the same thing and then try to solve the same kind of equation with a source. And the integral kernel that we need to introduce to solve the equation will be the propagator.
what's the source a function of? Because
It's a function of,
t, it can't be a function of my, like, if,
well, here, you mean in the case of Chern-Simons theory?
yeah, because somehow it has to be topologically invariant. Like,
Yeah, that's a great question. I mean, so I'm going to write down the source as being a closed two form.
okay.
But you're right in that the measurement I get doesn't change if I change it by an exact two form. But I'm not going to emphasize that point. So in fact, there's something similar here. I mean, on shell, I mean, sometimes two sources give the same measurement because there's, because of the equations of motion. I suppose I won't emphasize that. Like, for instance, if J was the Laplacian of something, then I could use the equations of motion to see that it would give me 0 on shell. There's going to be something similar in Chern-Simons theory, but I won't talk about it too much. OK, so how do we do this for Chern-Simons theory? If we want to write down something like integral of a dA minus a half a times j, well, then j should be a two form. If we want this to be gauge invariant, so under a small gauge transformation, like infinitesimally, the variation of A is A plus epsilon d chi mod epsilon squared. So this is the infinitesimal variation under a gauge transformation. Then for this expression to be invariant, we need ej is equal to 0. So what's the equation which we get? What's like the variational equation we get in the presence of the source? Is then that E of A is equal to J. On both sides, there are two forms. So this is a meaningful equation. Well, we'd like to, let's see, if we look back in this case, once I specify J and perhaps some boundary conditions, then this equation has a unique solution. However, this equation has lots of solutions because I can always, has gauge symmetry, I can always add a d of a function, and this equation will still be solved. So if we change a to a plus df d chi, the equation will still be solved. So to specify a particular solution of this equation, this equation has some gauge symmetry. But to specify a particular solution, I need to choose a gauge. in fact, everything I'm saying has a counterpart in Yang-Mills theory. If I was to introduce a source for Yang-Mills theory, then depending on how I introduced it, we would have had an equation like this, or perhaps star dA equals J. And then that equation would have many solutions, but you could fix a particular solution by choosing a gauge. Okay, any questions? So the gauge I'm going to choose is, we ask that sum of dxi ai equals 0. So I think this gauge in the physics, in the Yang-Mills case, is called Lorentz gauge. I can never remember the terminology. So this is like really the most natural gauge. So we'd like to, so the two equations that the gauge field must satisfy are then so we want A such that 1 dA is equal to J, and 2 sum del dxi of AI is equal to 0. And we want to write actually, before we go on, so we notice that so you might ask, why is this like, why are these equations strong enough? So if you combine these two equations together, this is an equation on the first partial. This is another equation on the first partials. You can use the fact that partial derivatives commute to get an equation on the second partial derivatives, which will be an equation a lot like the Laplace equation, which has a unique solution. So these equations together give you a very nice elliptic equation whose solution is unique given the source term and boundary conditions. So in any case, we want to write A of x as the integral over y of p x y j y, so that these equations hold. Okay, any questions? I'll put a wedge here. Now, let's think about what kind of tensor will P be. The J is a 2 form, and I want to do some integration over y. So it must have at least a 1 form here to be able to integrate over y. Then I want to end up with another 1 form, so I need it to be in total a 2 form. So pxy is a 2 form. On R3 cross R3 so that the integral over y, pxy, wedge j of y, is a one form. So the heuristic is here, this is 2 plus 2 is 4, and integrating over y eats 3. Leaves me with a one form. And then what equations do I want this to satisfy? D of A equals J will hold. Let's check this. If D of P for x, y is equal to the delta function at x equals y, viewed as a 3 form. Let me write this. So to see that, well, d in the x variable of the integral over y dx y wedge dy, I can move it across the integral. And then I can use the fact that the integral of a total derivative in the y variable vanishes. That's the integral over y of d in the x variable plus d in the y variable. So I think you should be able to see, yeah.
Why the last step is true? I mean the dy.
Because it's just the integral over y of dy of something. So by Stokes' theorem, we assume that everything vanishes at the boundary, or things decay rapidly in infinity.
Okay, yes.
Yeah, that's right. I should have made that assumption more explicit. The source must decay rapidly at infinity. Like the same thing holds over there for a scalar field. Okay, so the d in the x variable plus d in the y variable is just the de Rham operator in the x times y variables. So that's equals the integral over y of d. I'll just call it d, or d is dx plus dy of the propagator. And well, now I use the fact that there's a Leibniz rule. dp wedge j plus integral over y p wedge dj. And this term vanishes as dj is 0. And this term, if I assume dp is a delta function, delta x equals y times j of y, j of x. Okay. So the expression I wrote down, the delta decorated by the product of dx's minus dy's, is the form version of the delta function. It satisfies. It makes sure all the form indices behave correctly when I bring a compute as gx. Again, sorry if I was a little quick. Any questions? I always feel like when I prepare, I always don't think of all these details.
Yeah, because P is in some sense a non-local two form. I mean, it has dependence on both x and y.
Yes.
So when we write dp, we implicitly should be dx plus dy.
That's right, yes. But in fact, the correct propagator should have a symmetry between x and y. But actually, the dx and dy parts kind of look the same.
In that gauge, that gauge doesn't look very geometrical, like in the sense that there doesn't seem to be a.
It breaks the diffeomorphism symmetry. Yes, there's nothing you can do about that. Any choice of gauge breaks diffeomorphism symmetry.
Oh.
I think you can see this already. This is also true for Young-Mills theory. Classically, in dimension 4, it has conformal symmetry, but any choice of gauge will break that. Okay, so in order that the star of the integral over y dx, in order that A satisfies, I didn't introduce d star, sorry. Condition 2, we need the following. Sorry, I'm trying to think of a good way to write this second equation. Well, let me kind of cheat a little bit. We write P as PIJ xy dxi y dxj. Well, in principle, there might be other terms, but I'm not going to. So I'm going to be a little sloppy and not worry about the other terms, the dx dx and dy dy terms, because they don't actually play any role in that integral. Then P should satisfy sum d dxi pij equals 0. That's just the same equation, but now at the level of the integrand. This equation should hold for every j. Okay, any questions? Okay, so now we know what equations the propagator should satisfy. Let's solve them. So the unique solution to these equations with reasonable boundary conditions is B is epsilon ijk xi minus yi d xj minus yj wedge d xk minus yk over x minus y cubed. Okay, so I think what I'd like to do is explain why this expression satisfies the first equation that d of it is a delta function. Okay. And the fact that it satisfies the second equation there's some kind of explicit computation involved, but it's closely related to the fact that in dimension 3, 1 over r cubed is the Green's function for the Laplacian and is a harmonic function. Okay. Y is, actually, before I do that, let's think about how we can understand this better. So define a map from R3 across R3 minus the locus for x is equal to y to the two-sphere, call it alpha, by alpha of xy is x minus y over x minus y. And this is the same thing we did when we studied the linking number. We took two points, we looked at the line between them, and viewed that as a point of the two-sphere. So it turns out that this expression is the pullback of the volume form, the canonical volume form of the two-sphere. And P is alpha star omega, where omega is the SO3 invariant volume form. On S2. So to see that, I gave you an expression for this volume form last time. If we embed S2 inside of R3 with coordinates ui, then the volume form on S2 is epsilon ijk ui duj duk. So this expression is invariant under the group SO3 and restricts to give a volume form on S2, so it's the unique SO3 invariant volume form. Now if I pull it back under this expression, alpha star omega is equal to epsilon ijk xi minus yi over x minus y d xi minus yi over x minus y j, sorry, wedge d xk minus yk over x minus y. So with some small manipulations, you have to calculate, how do I differentiate 1 over or? So you know how to do that. You fiddle around with those calculations, you'll find it's what I wrote up to a factor. Times some constant. Okay. Okay. Any questions? Feel people are totally lost. Yeah. Okay. So there's some things you can have to believe. We haven't checked in detail. We haven't checked that it satisfies all the equations. But we see, we've sketched that it is the same thing you get when you study the linking number. This tells us that the linking number really is given by the integral. It really is given by the the two-point function in Chern-Simons theory. So maybe let me just explain why dp is a delta function. Well, this statement is, so first step, check that away from x equals y, dp equals 0. So this is just some calculation. So how do we do that? You think about what is dp? Well, I can apply d to this x minus y. I'll get the volume form divided by the radius cubed. Or I can apply d to the radius cubed, and then I'll get a similar expression. And you just have to calculate that the factors work out so that everything cancels. So now in round theory, the statement that dp is a delta function means that for all 3 forms, say omega on or3 times or3, that the integral of p wedge d omega is equal to minus the integral over the location of x equals y omega. So the reason these are the same is if I integrate by parts, I'll pick up a minus sign, and I'll pick up dp. Then I want to have dp times omega be the integral over x equals over the location or the locus x equals y times omega. So this is just like the definition of a delta function in the usual world of functions. So let's compute this integral. That's equal to so I can compute this integral as a limit as epsilon goes to 0 of the integral over the location where x minus y are separated of p wedge d omega. And then I integrate by parts. I bring the d over there. Well, that term vanishes. Then there's a boundary term plus the integral of the location x minus y is equal to epsilon p wedge omega. Now, p, so the locus where x minus y is equal to epsilon, this is OR3 times a 2-sphere. This is OR3 spanned by the center of mass times a 2-sphere, because these two vectors must be at a distance epsilon. And when I restrict p to this 2-sphere, it is a volume form. So p is 1 over x minus y cubed So on this sphere, this looks like 1 over epsilon cubed times the volume form which I inherited from flat space. So in other words, what we're finding is this expression is the average value of omega on a little sphere. So if that sphere becomes small, it just becomes the value at this location. Average value of omega on a small sphere and this converges as epsilon goes to 0, integral x equals y omega. Okay. Any questions? Yeah.
What happens if we want to consider triple functions? Is it possible to have a similar construction?
Consider which, sorry?
Sorry?
3-point functions.
Yeah, triple.
Absolutely, yes. So once we have the propagator, we're good. We can just do anything, right? We take a bunch of knots, and we connect them by propagators, and then the bulk lines, and the usual Feynman diagrammatics works. So the key point is we first need the propagator. Okay, any other questions? Okay, I'll stop there, and next time I wanted to discuss Feynman rules and non-abelian Wilson lines.